So far we have seen how to do numerical integration, in particular multiple dimensional integration, multidimensional integration numerically using the stochastic Monte Carlo integration based method. So far what we have been doing is we have been doing it in a very brute way. So, in order to get good converged value of the integral with few random numbers or few Monte Carlo steps, we need to improve the present or the existing method which we are doing. So, one such method which helps in improving the basically the sampling is called the acceptance or the acceptance rejection method. It is also called the hit or miss method. So, it is based upon the famous scientist von Neumann. So, let me try to explain what this method is through an example. So, the example which I will be using is basically an one dimensional integral. The reason I am using a one dimensional integral, though I have already said before that one dimensional integrals with Monte Carlo is not very efficient, is because one can then visualize the things much more clearly rather than trying to visualize or imagine a multidimensional space. So, what I am trying to do is I am trying to evaluate this integral I equals to integration 0 to 3 exponential x dx. So, this is the integral I am trying to evaluate. So, if I plot this function e to the power x, so what it will look like is the following. So, I have x here, y x axis here. So, at x equals to 0, so e to the power 0 is 1. So, it will go from 1 from here and it goes all the way up here. So, this is my x equals to 0 and this is my x equals to 3. Similarly, here my f x is equal to 1 and here my f x is equal to e to the power exponential 3. So, what is done in this method is, so I consider this rectangle. So, my rectangle is defined by x varying from 0 to 3, belonging from 0 to 3 and y belonging from 0 to e to the power minus 3. And then what I do is I generate two random numbers. I generate a random number x, which is 3 times my original random number. So, remember, so my Fortran random number generator returns me uniform distribution, set of random numbers with uniform distribution between 0 and 1. Okay. So, for my x, I need to scale this distribution from 0 to 3. So, I need to map this to a distribution to a set of random numbers which spans from 0 to 3. So, the way to do it is 3 into this random. Similarly, for the y also I need to map. So, this is for x. For y also I need to map this distribution to a set of numbers which lie between 0 to e to the power 3. So, what I do is I take y equals to exponential to the power 3 into my random number. So, now I have got two random numbers y and x. Then what I do is I check whether this random number y, the second random number which I have generated here, whether it lies inside this shaded area or it is outside. So, how do I check this? I use the if statement. So, I check if y is less than exponential x. The reason I am taking exponential x is because this curve is given by the equation e to the power x. So, if y is less than x, what it will mean is that the random number is somewhere in this shaded region and I include that number in my count. So, what I have to do is I have to keep a counter and to find out how many such random numbers are there in the shaded region. So, suppose such counter is given by s. So, I increase my counter to s plus s equals to s plus 1. So, I start with s equals to 0. So, I do this, I repeat this for say n number of times. So, what I will get is fraction of numbers that lie in this shaded region, which is my area of the curve, and that is given fraction of numbers in shaded region, and that is given by ratio of s by the total number. So, once I know the fraction of such points lying in the shaded region, so what I need to do is find out the area, so I need to multiply this fraction with the total area of this rectangle. So, then that will give me the estimate of this area covered under the curve. So, my value of the integral will be equal to 3, that is the length of the rectangle, into exponential 3, that is the breadth of the rectangle, and the fraction of points which falls under this shaded region. So, this is my estimate of the integral. So, the reason we are calling it as the acceptance rejection method or hit and miss method is because of the following. So, what we are doing is we are generating random number and then checking whether it is within the concerned area or within the concerned volume. If that particular random number do not lie within the volume of interest, or in this case the area of interest, we are throwing away that random number. So, we are accepting some and we are rejecting other, and as a result this method is called the acceptance rejection method. Rather than we generating a set of random numbers over all this area, we are just now using a fraction of them to evaluate the integral. So, this is what is the summary of the acceptance rejection method, but still as we will see that this method is also very brute in the sense you need to generate a lot. If your function is not a well behaved one, you need to generate still a large number of random numbers to have a reasonable estimate. So, now we will use the Monte Carlo integration. How using Monte Carlo integration we can numerically evaluate this integral. So, what we want to do is we want to find out the value of the integral e to the power x with a lower limit from 0 to 3. So, this we can solve analytically and we know that the exact value is e to the power 3 minus 1. So, what we will do is first we will just solve it with the trapezoidal rule and then we will use two different flavors of Monte Carlo. In the first flavor of Monte Carlo, this brute force Monte Carlo, we will just use the conventional philosophy that the integral of a function in mth dimension gives me the volume in that enclosed by that function in the m plus 1th dimension. So, that is what is this brute force Monte Carlo, and then we will again evaluate the same thing with the acceptance rejection method. So, let us first see the code for evaluating the integral within the trapezoidal rule. So, that is contained in this file called trap underscore x. That is content. Let us see what is the file name. So, okay. So, the file name is trap underscore auto underscore exp.f90. So, basically what I have done is I have used the same file with just modifying my function. So, this will be integration 0 to 3. Just to correct it, then we have e exponential x dx. So, this is the function which I am trying to integrate. As before, this part is all same. The only change which I have made here is I have changed the function. So, instead of evaluating the function 4 by 1 plus x square, what I will do is I will evaluate this function exp to the expx, and then rest part is completely same, and then I write down the bin size, the value of the integral as a function of the bin size, and also the error as a function of the bin size in this file with this name trap underscore exp.dat. So, let us run it and see what we get. So, as before, we compile it with my gfortran compiler, gfortran minus o trap underscore auto dot underscore exp dot x, then that is the name of the executable, and then trap auto underscore exponential dot f90. So, I have compiled it, and then I will now I am running it dot slash trap underscore auto underscore exponential dot x. So, I give the starting value of n. Let me start with a small value, say 10. The limit of the integral, if you remember, it is from 0 to 3, as I have written it here, 0 to 3. So, the lower limit is 0, the upper limit is 3. So, it will take some time to evaluate, and then so we have to wait till it is done, because it is doing for several values of the integral. So, now it is done, and then what I have is the file containing the data trap exp underscore dat. So, like before, if I see what are the contents of the file, let me just grab them out, and this is what I get. So, these are the okay. Now, here I do not have it as a bin size, rather I have written it as a function of the number of grid points. So, as I increase the grid points, you see that the error is decreasing very fast. Okay. So, with 100 grid points, I am already doing very good with a error of 10 to the power minus 3, but the moment I went to this grid size, the error decreases to 10 to the power minus 12. Now, the same thing, how will I do it using Monte Carlo integration? So, the code that does that is the following. So, the name of the code is crude Monte underscore MC underscore int underscore exp. So, let us open this file. So, again here in the comment line I have to correct this. This is integration 0 to 3, then I have exponential x dx. Okay. So, what I have here is I have two integers. The n is the number of points. Now, remember, unlike the trapezoidal rule, these points will be random points, which will be given by, which will generate by using my random number generator, and I is the counter. P is the dummy variable used for the subroutine called random underscore number, which returns the random number when I call this random number generator. Crude underscore MC is the variable where I am storing the value of the integral. Then x is a number which basically lies between 0 to 3, and then I have my function. FUNC is a function, as we have seen before. which evaluates the value of the function e to the power x when I give a value of x. And then what we have is then sigma stores the value of the sigma, var stores the value of the variance, length stores the total length of the interval over which we want to do the evaluate the integral, and since here it is done from 0 to 3. So, I have set length to 3. Again I am using double precision here, and actual stores the actual value of the integral, and the actual value of the integral, as I mentioned before, is exponential e to the power 3 minus 1. So, this is my actual value of the integral. Again I do it for several value of n. So, I want to store the data, I want to store the value of my integral as a function of different values of n. So, that information is stored in this particular file. So, how do I do it? So, first I set this crude underscore MC, where I will be storing the value to 0 and sigma to 0. So, once I do that, what I do is I follow these steps n number of times. So, each time what I do is, so basically what here I am doing is I am computing the average value of the function, but instead of taking a fixed grid, I am taking the grid is a random one depending on the random numbers which is returned by my random number generator. So, and also remember that this random number generator, what it does is it gives me random numbers from 0 to 1. So, that random numbers from 0 to 1 I need to distribute it from 0 to 3, and this is how I do it. I just simply multiply it by 3 times the random number p, where p is a random number which lies between 0 to 1. So, this is my new grid point x, which I find it this way, and once I find it this way, then what I can do is I can evaluate using the function. I can evaluate the value of the function at this particular x point. Similarly, and then I keep on adding it up, and similarly for the sigma also I do the same thing, but sigma it is the square of the function which I need to do. So, because this one the integral is the average, now I am computing this I want to compute the variance, and so I need to sigma, which is the average of the square of the function. And once this do loop is executed, what I do is to compute the average, I need to divide it by the real n. Here is the number of times I compute the value of the function. Similarly, for sigma, and then my integral, the actual value of the integral, I need to multiply it by the volume of which in this case, since it is a one dimensional, it is a length. So, length into crude underscore MC, and similar way I also compute my variance, and once that is done, I write it here in the screen, and I also write the error in the file, the value of n, the number of iterations or the number of times I am evaluating or the number of random numbers I am using to make this estimate, and then the crude value of my integral, and then the error compared to the actual value of the integral. Once this is done, what I do is here I change n to n into 10, I increase it by tenfold, and then until and unless the n is, or as long as n is less than this number, I repeat this whole steps. So, I go back to this point, go to 7, 7 is this point. I again set my this crude underscore MC and sigma to 0 and repeat all the steps. So, once this is done, then it will come out of the loop. So, let us again compile and run the code and see what happens. Crude MC integration. Oops. Sorry, I missed the minus O thing. Okay, so it has produced this executable file, this one here. So, let us run this. Okay, so I start with a very small value, say 10, and then it automatically does for several values. So, to wait for some time for it to come out of the loop and do the and finish the calculation. Okay, it is done. So, if I do ls minus lt here, so I have this file which has been produced, which contains the value of the integral as a function of the number of random numbers I use to compute the average. So, if I do it, so this is what I get. Now, let us compare it with my trapezoidal rule. So, this first part here is the output of the value of my integral as a function of n using the crude Monte Carlo, and this one here is the value of the integral for the same thing using the trapezoidal rule. So, what we see is that in comparison to this Monte Carlo simulations, Monte Carlo integration here, the accuracy achieved by the trapezoidal rule is much higher. But this is true because I mean this is in a one dimension, and in one dimension typically your trapezoidal rule is much better and much more faster also compared to the Monte Carlo integration. So, now we will do the same integration using the acceptance rejection method. So, in the acceptance rejection method, what one needs to do is, so this is the integral which I am evaluating. So, basically what I will do is I will consider a square whose origin is which are formed along the x direction, it goes from 0 to 3, and in the y direction it goes from 1 to e to the power 3. So, what I will generate randomly throw points inside this particular square, and then I will find out how many points are there which lies within this curve. So, that fraction gives me the value of the integral. So, again as before, what I have here is integer variable set of integer variables. I start with I, the counter, then I have n, which gives the total number of points, and then I and this pt underscore curve will calculate how many points that lie within the curve. Then I have the value of x, and then p is the dummy variable for my random number generator, y is the value of the function, and integral is the value of the integral, and then exact is the value of the analytical value of the integral. So, I ask the user to send me the value of n, and since I want to do it again for several values of n and do it in automated process, and I stored them here. So, I set the counter to the number of points that lie within the curve to be 0 each time I want to evaluate this integral for each value of n. Then what I do is, the first step is I find a random value of x between 0 and 3, and this is done by these two lines. So, first I call a random number, my random number generator, which gives me the value of a number between 0 and 1, which I convert to, which is stored in p, and this number I convert to a number between 0 and 3 by multiplying it by 3, and I store it in x. So, once that is done, then I evaluate the value of the function at a random point between 0 and e to the power 3, which exponential 3, which is the maximum value of the function. That I do it in a similar way as I have done to find a random number x. So, I call a random number p, which lies between 0 and 1, and then I multiply the random number to e to the power exponential 3.0. Now, once I have got these two numbers, what I do is I check whether this random number y, which is the value of the function, any value of the random value of the function that lies between 0 and e to the power 3, whether it is less than that particular the random number x, exponential of the random number x. If it is so, then we can assume that then we can consider that the point lies within the curve enclosed by or the area enclosed by the curve, and I count it. So, I repeat this process several times, and I count, say if I throw 1000 times such numbers on my square, how many such numbers lie within the area enclosed by the curve. So, once I know it, then I can compute the integral in the following way. So, this gives my, so this part is basically the fraction of the points which lies within the curve, and then this is the area under the curve. So, if I do the integral, and then what I am doing here is I am also evaluating the exact value of the integral, and then I am writing it in this file. So, and then as before I am automating the process, and it is done till the n takes a value of which is larger than this one. So, let us compile it as before and see what we get. So, I start with a very small value and let the code run. It will take some time to run it. So, once it is done, so what we will do is let us see what is the file. So, you see it has produced this particular file. So, let me just copy it and let us see what it has done. So, these are the set of numbers. So, see again this method also, the accuracy is, even with such a huge number, the accuracy is few orders of magnitude worse than what we achieved with the trapezoidal rule. So, okay. So, this is how one does the integration using the acceptance rejection method and the crude Monte Carlo, and we have also seen how these compares with the trapezoidal rule for a low dimensional case. So, for a low dimensional case, definitely the trapezoidal rule works much better.